Hello. In today's session, we are going to discuss some properties of prime numbers that will lead us to one of the most important results in number theory, known as the fundamental theorem of arithmetic. The first result that we are going to see is the following. If P is a prime, and P divides AB, then P divides A or P divides B. This is the first results that we want to verify. That means if P divides a product where P is a prime, then P divides one of them exclusively. Note that this statement is not true if P is not a prime. For example, we know that 8 divides 4 into 2. So here we can take this to be some C, this to be A, this to be B. So C divides AB, but we cannot say that 8 divides 4 or 8 divides 2. Therefore, the statement is true only if we have P a prime. So of course, it can happen that in some cases C dividing AB implying C dividing A or C dividing B. But what we want to say is C divides AB in general need not imply that C divides A or C divides B unless C is a prime. Okay. The proof of this result is quite easy, provided we use one of the previous results we have already seen. So we are going straight away to the proof. So we have to show here that P divides A or P divides B given P divides AB. So this is already given, P divides AB and P prime. This thing is not. Suppose that P does not divide A. So we have to show that one of these definitely happens. Either P should divide A or P should divide B. Suppose that the first case is not happening, that is P does not divide A. So to show that what we claimed is true, we must show that P divides B. Suppose P divides A, then we are done. Why? We want P to divide either A or B. We are not interested in checking if P divides A and B. We want P to divide one of them, that's it. So if P divides A, then there is nothing else to prove. We already got that P divides one of the numbers, we stopped. Okay, now suppose P does not divide A. This is the case that we want to see. So we have to show that P divides P in this case. Okay, P does not divide A. So what we can say about the GCD of A and P? Suppose GCD of A and P is D some positive integer, then being the GCD, D is a common divisor of A and B. D divides A and D divides P. But what are the only divisors of prime P? P has only two divisors, 1 and P itself. Therefore, D equal to 1 or P, because P has only two divisors, 1 and P. Therefore, D must be equal to 1 or P. But according to our assumption, D cannot be equal to P because P does not divide A, but D divides A. Therefore, D cannot be equal to P, and so D must be equal to 1. Since D divides A and P does not divide A, D is not equal to P. Therefore, the only possibility remaining is D must be equal to 1. So D is equal to 1, that is GCD of AP equal to 1. Now recall the result that we have already seen. What is the result? If AB equal to 1 and A divides BC, then we have seen that A divides C. We are in the similar situation. Here PA equal to 1 and P divides AB. So what we can say from the above statement, AB is equal to 1, A divides BC implies that A divides C. So PA is equal to 1, P divides AB, therefore P divides B. So if P does not divide A, P divides B. Therefore either P divides A or P divides B. Therefore if P does not divide A, then P divides B. Therefore P divides A or P divides B. So we are done. We can extend this statement, that is P divides AB implies P divides A or P divides B. We can extend this statement for any finite number of any product containing finite number of elements. So the statement is the following. So the general statement is the following. Let P be a prime, as in the previous case, A1, A2, etc. An integers such that P divides A1 into A2 into etc. An, the product. Then P divides AI for some I in 1, 2, etc. n. That means either P divides A1 or P divides A2 or P divides A3, etc. P divides A. P must divide one of the elements in this product. This statement we can prove using induction. Proof using weak induction. Okay, so when n is equal to 2, that means P divides A1, A2. Case n equal to 2, that is the first case. P divides A1, A2. But this case we have already seen, because P divides AB implies P divides A or P divides B. So P divides A1 or P divides A2 by the previous theorem. This is not worse. Now assume that our claim is true for n equal to m that is greater than or equal to 2. So assume that our claim is true for some n equal to some m that is greater than or equal to 2. We will show that our claim is true for m plus 1 also. That is, this claim is true means P divides A1, A2, etc. Am implies P divides A1 or P divides A2 or etc. P divides Am. Assume that this is true. Okay. Now we are going to look at the product A1, A2, etc. Am plus 1. Suppose P divides A1, A2, etc. Am plus 1. Now we are going to split this product into two products. P divides A1, A2, etc. Am, that is 1, and Am plus 1. Now this is of the form AB. P divides AB, where A equal to A1 etc. the product of A1 A2 etc. AM, B equal to AM plus 1. But again, using the previous theorem, we know that P divides A or P divides B, but B is AM plus 1. But what is A? A is A1, A2, etc. up to AM, and by our previous assumption, the assumption we have taken is P divides A1, A2, etc. up to AM implies P divides A1 or A2 or etc. AM. So we can club these two together. Therefore, P divides A implies this part implies A1 or A2 or etc. P divides AM. These things are given by P divides A, and for up to AM, if you are taking M elements in the product, it's true. And this is also there, or P divides AM plus 1. This is what we want. So we establish in the general case that if P divides a product of numbers, then P divides at least one of them. Now we are moving to the most important result that we promised to give, that is the fundamental theorem of arithmetic. So the statement is the following. Every positive integer n greater than or equal to 2 is either a prime or a product of primes with the primes appearing in the product unique up to the rearrangement of primes. So the meaning of this result is the following. Suppose that n is greater than or equal to 2. So then n is going to be equal to a prime, or n equal to p1, p2, etc. pk, a product of k primes. And not only that, if n we write as q1, q2, etc. qs, then this p1, p2, etc. pk and q1, q2, etc. qs, they are going to be exactly the same primes, except possibly some shuffling of the order in which the primes are appearing on both sides. That means it is not necessary that p1 is going to be equal to q1, p2 is going to be equal to q2, etc. But it is necessary that k is going to be equal to s. So in any representation of n as a product of primes, the primes appearing and the number of prime factors appearing are unique. That's what the fundamental theorem of arithmetic says. So we are going to prove the fundamental theorem using strong mathematical induction. In fact, the first part. What is the first part? In the first part, we have to show that given any integer n that is greater than or equal to 2, it is either a prime or product of primes. The uniqueness of primes appearing in the product, in this product, we will prove as the second part. So part 1 is the following. Every integer n greater than or equal to 2 is a prime or product of primes. So we are going to prove strong mathematical induction. So if n is equal to 2, so to prove using mathematical induction, we must have an initial step, and we must have the induction statement also. So Pn, the induction statement, suppose that Pn is the induction statement, and the statement is the following: n greater than or equal to 2 is a prime or product of primes. This is the induction statement we have. So what is P of 2? P of 2 is 2 greater than or equal to 2. 2 greater than or equal to 2 is just 2. 2 is definitely greater than or equal to 2. 2 is a prime or product of primes. Is this true? If this statement has to be true, then either 2 is a prime should be true, or 2 is a product of primes must be true. But we know that 2 itself is a prime, therefore this part itself is sufficient for us. This is true, therefore P of 2 true. Now we are going to assume that P of 2, P of 3, etc. to P of m is true, and we will prove that P of m plus 1 is also true. Assume P of 2 we have already verified, in fact, etc. to P of m true. To prove P of m plus 1. Okay, we are going to prove P of m plus 1, assuming that P of 2, P of 3, etc. P of m are true. So P of m plus 1 is what? M plus 1 is greater than or equal to 2. Okay, we will write P of m plus 1 is the following. M plus 1 is anyway greater than or equal to 2. M plus 1 is a prime, or m plus 1 is a product of primes. This is P of m plus 1. Now, if m plus 1 is a prime, there is nothing to prove, because that's one of the things that we wanted. If m plus 1 prime, we are done. P of m plus 1 is true. So if m plus 1 is not a prime, then only we need to proceed further. Suppose m plus 1 not a prime. If m plus 1 is not a prime, then m plus 1 is a composite. That means m plus 1 can be written as a product of the form sum k1 into k2, where k1, k2 are not 1, not m plus 1. Therefore, there exists k1, k2 with 1 less than k1 and k2 less than m plus 1, and m plus 1 equal to k1, k2. Now we know that k1 is strictly less than m plus 1 and k1 is greater than 1. Therefore, P of k1 and P of k2 are true, because k1 is from 2 to m, k2 is also 2 to m. Therefore, k1 is a prime or product of primes, and so is k2. k2 is a prime or product of primes. So if k1 is a prime or product of primes and k2 is a prime or product of primes, then the product of k1 k2 is again going to be prime into product of primes or product of primes into primes. Anyway, everything is going to give only primes. Therefore, m plus 1 equal to K1, K2 is a product of primes where the primes are coming from K1 and K2. Therefore, P of m plus 1 true, but P of m plus 1 true given P of 2 etc. P of m true and P of 2 itself is true. Therefore, P of n true for any n greater than or equal to 2. That means every natural number greater than or equal to 2 is either a prime or product of primes. So we establish the first part. Now we move to the second part. What is second part? First part we will just write every integer greater than or equal to 2 is a prime or product of primes. So first part is established. Now we move to the second part. What is the second part? We have to show that the product of primes appearing in n. Of course, if n itself is a prime, there is no way to write n in two ways. If n is a product of primes, then the primes appearing is unique. Second part is this: if n is a product of primes, then the primes appearing in the product is unique up to reordering of the primes. That is, for example, suppose that we consider 12. We know that 12 is equal to 2 into 2 into 3. But 12 we can again write as 2 into 3 into 2. But here the primes appearing in both these are the same, and each prime is appearing in both these representations the same number of times. That is what's meant by saying that the product, the primes appearing in the product is unique up to reordering of the primes. Okay. Once again we will try to use induction to prove the uniqueness of this factorization. So this can be termed as the uniqueness of factorization. In fact, I forgot to mention that the first part is actually the kind of existence part, where we are proving that n can be written as the product of primes if n itself is not a prime, and second part is the uniqueness part. So fundamental theorem of arithmetic has two parts. One is the existence of product of primes, and second is the uniqueness of the primes. So it has two parts. We are going to the second part. We are going to use induction once again here. So if n is equal to 2, so P of n is the statement here that prime factorization of n is unique, where n is of course greater than or equal to 2. We know that P of 2 says that prime factorization of 2 is unique, but prime factorization of 2 is just 2. 2 can be written in only one way as product of primes. This is not actually a product of primes, but we may say, if you want, that it's a product of just one prime. So P of 2 is true. Now what is next? Now we have to verify that P of k plus 1 is true, assuming that P of 2, P of 3, etc. up to P of k are true. Assume that P of 2 extra P of k are true. We will prove the statement P of k plus 1 is true. Okay, for the sake of avoiding some confusion, we may probably rearrange the primes appearing in two representations of the given n in such a way that the primes are appearing in the increasing order. So, suppose P1, etc., PR and Q1, etc., QS are primes with P1 less than P2 less than etc. less than PR, Q1 less than Q2 less than etc. less than QS. Suppose that we are arranging them in the increasing order, and what is the relation between n and these primes? N is written as the product of these in two different ways: P1, P2, etc. PR, and n is equal to Q1, Q2, etc. QS. Sorry, this is not n. We are trying to prove this for k plus 1. Okay. Now, we have seen that P1 divides P1 into P2 into etc. PR. So P1 must divide Q1 into Q2 into etc. QS also. P1 divides P1, P2, etc. PR implies, since this is equal to Q1, Q2, etc. QS, P1 divides Q1, Q2, etc. QS. Okay, now P1 dividing a product of numbers implies that P1 divides at least one of them. So P1 divides Q1, or P1 divides Q2, or etc. P1 divides QS. So we will remove P1 from both sides. So we will have k plus 1 by P1 equal to, we don't know, see, one more thing is P1 and Q1, Q2, etc. are all primes. Therefore implies that P1 is equal to Qi for some I in 1, 2, etc. S. Because if a number P1 is a prime and the Qi's are all primes, therefore a prime dividing another prime implies that they must be the same. So P1 must be equal to Qi. So k plus 1 P1 is going to be equal to P2, P3, etc. PR. This is equal to Q1, Q2, etc. Qi minus 1, Qi plus 1, etc. QS. Now the problems comes, we have to look at this carefully. K plus 1 by P1 is less than K plus 1 by P1 is less than K plus 1. Therefore, by the induction assumption, and what about, is this going to be greater than 2? Is this going to be greater than or equal to 2? Because if this is not greater than or equal to 2, then this is going to be equal to 1. If this is equal to 1, then P2, etc. PR are all 1. And then Q1, Q2, etc. QS are all 1. There are no other primes remaining. Therefore, 1 equal to 1. So we have already proved that P1 is equal to Qi. Therefore, on both sides, P1 is there, and on the other side, Qi will be there. If K plus 1 by P1 equal to even that is not necessary. If this is equal to 1, okay, if this is equal to 1, then there are no primes. Here there are no primes. Here also there are no primes. Then we have k plus 1 equal to P1 equal to just Qi. But P1 equal to Qi, that means that there is only one prime on both sides and they are the same, therefore we are done. So assume that k plus 1 by P1 is greater than or equal to 2. But it is already less than k plus 1. Therefore 2 less than or equal to k plus 1 by P1 less than k plus 1, and therefore by the assumption, what is the assumption? So the assumption is that P2 etc. up to Pk are all true, and now k plus 1 by P1 is less than k plus 1, or we may even write here this is equal to less than or equal to k. Therefore k plus 1 by P1 will be having a unique representation as product of primes. Therefore P2 etc. up to Pr and Q1 Q2 etc. Qi minus 1 Qi plus 1 etc. up to Qs, they must be the same. Therefore P2 etc. Pr and Q1 etc. Qi minus 1 Qi plus 1 etc. Qs are same primes appearing possibly in different order. So Q2 etc. Pr, Q1 etc. Qs, they are all same primes, same number of primes appearing in different order. Therefore we have, if we reshuffle them, that means that we have P2 etc. up to Pr, and these two combinations are exactly the same, these two primes are exactly the same. Therefore k plus 1 by P1 is equal to P2 into etc. Pr is unique. There is no other representation possible. Therefore what about k plus 1? So k plus 1 is just obtained by just moving this P1 to the right side. P1, P2 etc. Pr is also unique. So we established that k plus 1 is also having a unique representation as product of primes. Therefore P of k plus 1 true. So by induction, by strong induction, P of n true for any n greater than or equal to 2. That means any integer greater than or equal to 2 is either a prime or a product of primes, and the primes appearing is unique up to some reordering of the primes appearing. That's what the fundamental theorem of arithmetic says.